Hello everyone, this is lecture 2 of course PE 500. In the previous lecture, in this course, we have introduced the meaning of calculus and the subcategories of it, differentiation and integration, and we introduced the basics of each of them and the main idea behind them. We have also introduced multiple applications to understand the meaning of differentiation and integration. Simply, in differentiation, you aim to get the rate of change of a simple function, assume f of x, at a specific point, and we understood that if we have 2 points at a distance h, if we decrease that value h to be a very minimum value, so it approaches the main point, so we can get the tangent of that point, which is the rate of change at the same point. In differentiation, there is something called differential equation. And differential equation is an equation that relates a function to its derivatives, which captures how one quantity it changes with respect to another. So we have an equation that contains a quantity, and we need to capture how that quantity changes with respect to another. So these equations, which are differential equations, are important during your modeling as the quantities evolve over time or space. For example, the chemical reactions, the saturation, for example, evolve over time. So we need to capture how the quantity it change with respect to another in that chemical reaction. The same in biological populations or mechanical systems. Differential equation can be divided into two subcategories: ordinary differential equations, or ODE, partial differential equations, or PDE. In ODE, we have derivatives, but it's reflecting a single variable. In PDE, we have partial derivatives with respect to multiple variables. So if you find in a specific equation that you have a single variable in the derivatives, then this is called ODE, or ordinary differential equation. And if you find multiple variables and partial derivatives in the equation, then this is called partial differential equation. So why differential equations are important in biology? Simply, in biology, differential equations are used to model dynamic processes such as bacterial growth, enzyme kinetics, and heart rate regulation. All of these provide quantitative insights into these systems. So we need to understand how the different rates influence the outcomes. For example, how the absorption of a specific drug to a human can affect the growth of a tumor or the spread of a disease. So if we have a differential equation and we solve it, so we can predict future states of this biological system. And based on that, we can design and control the behavior of these systems. So the aim now is that we have a differential equation. We need to understand this differential equation and categorize it correctly, as we are going to see in this lecture. And based on that categorization, we will know how to solve it. So we can convert it from a differential equation to a normal equation in the time domain, for example, and based on the retrieved equation, we can predict future states of the system. So we need now to understand the classifications of the differential equations. We mentioned the difference between ODE and PDE. There is two other taxonomies: linear and nonlinear, autonomous and non-autonomous. Let's start again with ordinary differential equation and partial differential equation to understand the meaning behind each of them and introduce different examples. In ordinary differential equation, we have derivatives with respect to a single independent variable, which is commonly the time, t. For example, in this equation, we have a single variable, which is p, which represents the population size, and r here is a constant, which is the growth rate. So in the whole equation, we have derivatives that reflect a single independent variable, which is the population size. So this can be considered an ordinary differential equation. In partial differential equation, we have partial derivatives with respect to multiple independent variables. For example, time t and space x. So if you find a differential equation that contains the derivatives of two or more independent variables, then this will be a PDE function. For example, the heat function involves how the temperature U, which is here, evolves over time and space in a medium. So we have now U with respect to the time and U with respect to the space. PDE are critical in fields like diffusion, wave propagation, and fluid dynamics, where you can find them in biological contexts such as nutrient transport or electrical signal propagation in neurons. So we have many applications related to ODE functions and PDE functions. And the aim is to check the equation, determine that if it's ODE, then there are different ways to solve the ODE functions, and if it's PDE function, then there is other ways to solve them. When we learn these ways, if you tried to use the different ways to solve ODE to solve a PDE function, then you may not reach a solution. The second classification is linear and nonlinear differential equations. So to determine that a differential equation as a linear if the dependent variable y and the corresponding derivatives appear linearly. This means that all of them are raised to the power of 1 and there are no products or higher powers. For example, there is no y square, no y cubic, and so on. There is a general form to determine if this equation is linear or not. The equation is the derivative of order n, and we will understand the meaning of the order after a while, multiplied by a factor, which is a constant, or an equation of x or other variables rather than y. The same here, multiplied by a factor, and so on until you reach y multiplied by a constant or an equation of x. And the other side of the equation is a function or another function of x. So if you look here, is that all of these are coefficients that may depend on x, and they may be constants. And also g of x is a function of x. If you find that an until a naught or g of x contains a factor of y, then this will be a nonlinear differential equation. In this example, we have dy by dt multiplied by 1, which is the derivative of y with an order 1, and 2 multiplied by y. So a naught here will be 2, and y, which is here, and g of x will be e raised to negative t. So the coefficients here doesn't contain y, and the function here doesn't contain y. So this will be a linear ordinary differential equation. And why it's ordinary differential equation? Because we have a single variable, which is t. As we mentioned, this equation can be solved analytically in many cases using standard methods, such as separation of variables and integrating factors. And we will introduce these methods in the following lecture and how we can solve the ordinary differential equation or the linear differential equation using these methods. Second, a nonlinear differential equation has the dependent variable y or its derivative appear nonlinearly. And here you will find that the variable y or the corresponding derivatives are raised to powers other than 1, multiplied together, or involved in transcendental functions. And these functions are class of mathematical functions that are not algebraic, such as the logarithmic, sine, and cosine. Let's check this function. We have dy by dt, and this is not a multiple of y or raised to any power, so let's ignore that one. Let's check this one. This y is raised to the power of 2. Then by finding that, then the whole equation will be nonlinear. So if we try to solve this equation using the traditional ways to solve linear ones, then it will be difficult or impossible to find solutions. In these cases, there are numerical methods to approximate the solutions. So based on the taxonomy or the classification, whether it's linear or nonlinear, then you will find or categorize the ways to solve each of them. The last classification is autonomous and non-autonomous. And autonomous differential equations doesn't explicitly depend on the independent variable, which means that the equation remains the same regardless of the time or space variable. If you check this equation, you will find that r, k are constants, and we have a variable p with respect to the time, and b here, p here. So there are no other variables that explicitly depend on the independent variable, and in this case, this function is autonomous. Non-autonomous differential equation is the opposite, where these equations depend on the independent variable, reflecting external influences on the system. Let's check this function. We have the variable p with respect to the time, and p is here also, and we have another function, not a constant in this example, that depend on the variable t. So in this case, r, it changes with respect to the time. So we have another variable that depend on the independent variable, which is t. Then in this case, it's non-autonomous. So if we write the equation like that, r is a constant, p, in this case, this will be autonomous. And if we write it like that, r, it changes with time. In this case, this will be non-autonomous. So depending on the variables or constants in your equation, you need to check if it's constant or it varies depending on the independent variable. If so, then in this case, it will be non-autonomous. Now, we need to classify the following examples, whether they are ordinary or partial, linear or nonlinear, autonomous or non-autonomous. So let's begin with the first example. dp by dt equal to r multiplied by p. Here, r is a constant, and we have a single variable, so this will be ordinary differential equation. R is a constant, and we have only the p that depends on time, so it will be autonomous. And also, p is not multiplied or raised to any powers, so this will be linear. The second example, dx by dt, the second order, equal to omega square multiplied by x. This is an extra. So in this case, this is a constant. We have x, which in this case not raised to any power or multiplied, so this will be linear. We have a single variable, so it will be ordinary differential equation, and no variables that depend explicitly on the independent variables, so this will be autonomous. The third equation, dp by dt equal to r, which is constant, p, which is a variable, 1 constant minus p, which is a variable, k is a constant. So in this case, we have a single variable, so it will be ordinary differential equation, and there is no explicit independence on the independent variable, so it will be autonomous. And to determine that it's linear or non-linear, then we need to check if there are any powers or multiplications to the same variable. From the first sight, you may say it's linear, but let's check. If you multiplied all of them together, then it will be r multiplied by p multiplied by 1, so it will be rp minus rp multiplied by p over k, so it will be rp squared over k. So in this case, p is raised to the power of 2, so it will be nonlinear. The fourth equation is a partial derivative of two variables, u over t, or du by dt, and du by dx. So we have two variables, t and x. In this case, it will be partial, and it's not raised to any power, so it will be linear. And here, to determine its autonomous or none, we need to check if there is a dependence on the variable t or not. So this function explicitly depends on the variable t, so it will be non-autonomous. The same for this equation. It's a similar but with a different constant. Don't be tricked by this constant because it will remain a constant, whether it's raised to the power of 2 or 3 or whatever. So it will be partial differential equation, linear and non-autonomous. The sixth equation is dv by dt, and we have here natural logarithm, and we mentioned that to determine its linear or non-linear, so we need to check if there are transcendental equations raised to the power of 2 or n rather than 1, or multiplied by the same variable. So we have here natural logarithm. So in this case, it will be nonlinear. R is a constant, V is a variable, R is a constant, K is a constant, so it will be autonomous. And there is only one variable, so in this case, it will be ordinary differential equation. The last one, we have two variables, X and T, so in this case, it will be partial, linear or nonlinear, depending if there are any power or multiplied by a factor, or there are any functions such as natural logarithm or sine and cosine. If you check this one, you will find the u is multiplied by du by dx, so there is a product here, so it will be nonlinear. And in partial differential equations, they depend on the variable t explicitly, so it will be non-autonomous. So this will be the solution of the different examples. Now let's move to the second part, which is determining the order and degree of differential equations. So let us start by the order. From a while, we mentioned that there's a second order of a differential equation, and we mentioned that we will define the meaning behind that after a while. And here we are. If we have a function, let's say y equals to x cubic, and I asked you to find the first derivative of it, or apply differentiation on it, simply by revising the different rules of the derivatives. We have x to the order of 3, simply y dash, or the first derivative will be put 3 here, multiplied by x raised to the power of n minus 1, so it will be here 2. This is called the first derivative, or the derivative of order 1. If I asked you again to take a second derivative, then it will be y double dash will equal to a constant multiplied by something raised to a power. So take the power multiplied by x, n minus 1, it will be 1, so it will be 6x. In this case, it will be the second derivative, or a derivative of order 2. If I asked you again to take a derivative, so it will be y triple dash will equal to 6. So in this case, it will be a derivative of order 3. So the order here of an equation is determined by the highest derivative present in the equation. So if you have this plus this plus this plus that, so the whole differential equation has an order of 3. For example, in this equation, this has an order of 1, order of 2, or this is the first derivative, the second derivative. So in this case, it will be order 2. To reflect that biologically, in first order equations, you will find them modeling the rates of change, such as growth rate, reaction rate, and so on. But in second order equations, you may find them describing acceleration or curvature in biological systems, such as the oscillatory behavior in heart rate dynamics. What about the degree? The degree here is the power of the highest derivative. So we need to check the power of the highest derivative, not any derivative. So the degree provides additional information about the equation's structure. For example, in this equation, it has an order of 1 because the highest order is 1, but it has a degree of 2 because the highest order, or the highest derivative, has a power of 2. So it will be order of 1, degree of 2. So there is a difference between d2y by dx square and dy dx, the whole is square. In this one, it's an order of 2, degree of 1. Order of 2, degree of 1. In this case, order of 1, degree of 2. In higher order equations, you may find higher order equations in nonlinear systems, such as the predator-prey models, where interactions between species lead to complex behaviors. Let's reflect that using examples. This equation, we mentioned it's an ordinary differential equation. It has order of 1, or first order, and also it has a degree of 1. In this equation, it has order of 2 and a degree of 1. In this equation, it's a first order and first degree. So what is the importance of order and degree? Understanding both of them of a differential equation, it can help determine the complexity of the system being modeled. And based on that, it can guide to the choice of the solution methods, whether you are using analytical methods or numerical methods. As mentioned, ordinary differential equations are used in bioengineering for modeling temporal changes such as enzyme kinetics, pharmacokinetics, and population dynamics. PDE are critical for spatially distributed systems such as diffusion of nutrients in tissues, heat transfer in organs, or electrical signal propagation in neurons. First-order equations are often sufficient for simple cross or decay models, while higher-order equations capture more complex behaviors such as oscillations or interactions between multiple variables. The degree of an equation provides insights into the system's nonlinearities that can significantly affect the behavior and stability. So you need to understand how to classify a differential equation, and based on that classification, let's say we have a simple equation, ordinary differential equation with a first order and first degree. So from that, we can say this equation may be found in a simple cross or decay model, or because it's ordinary differential equation, it can be used or it's found in modeling temporal changes such as enzyme kinetics. So based on that, you can reflect the meaning where we found that equation. So simply, the aim is that we have a system where we modeled it to a differential equation and we need to solve that equation. So before solving the equation, we need to understand the category of it, whether it's ordinary or partial, linear or non, first order, second order, first degree or second degree, and based on the whole taxonomy, we will determine that we will use this specific method, or we will ignore the analytical approaches and reflect or use the numerical approaches. Now, let's solve this example. We need to determine the order and degree of each of these examples. In the first example, it's an equation. It has dy by dx, which is the highest derivative. It has a power of 1, so it's a degree of 1. And we have only dy by dx, which is the highest derivative, so it's the first derivative, so it's order of 1. In the second example, there is the highest derivative, which is d squared by dx, which has an order of 2, and the highest derivative is raised only to the power of 1, so it's a degree of 1. In the third example, we have the highest derivative, which is here, which is 3, so it will be order 3, and the whole derivative is raised to the power of 2, so it's a degree of 2. In the fourth example, this is the highest derivative. It has order 4, and the whole is raised to the power of 1, so it's degree of 1. In the last example, the highest derivative is order of 2, and the whole is raised to the power of 3, so it's a degree of 3. So in this lecture, we have introduced the different classification of a differential equation after understanding the meaning of a differential equation. The classification is subcategorized into 3 things: ordinary differential equation and the partial differential equation, linear and nonlinear, autonomous and non-autonomous. Then we introduce the difference between an order and degree of a differential equation. So simply, you can get an equation and you will be asked to find whether it's ordinary or partial, linear or non, autonomous or none, and also find the order and degree of this differential equation.